if we had a series of numbers that increased like this, 2, 4, 6, 8, what we might notice about them is that each of these numbers is increasing by the same amount each time. This is an example of an arithmetic progression. So you can see the first value, which we would say the n equals 1 value, is 2, and then the next value is 4, and then the next is 6, and on and on and on. What we could do here is we could use a notation that enables us to represent certain things. For example, we could say A is the start value, which in this case is 2. And we could say that the difference each time, D, is equal also to 2 because it's increasing by 2 each time. Furthermore, we could talk about the number in the sequence that we're on. We could talk about this one as n equals 2, this one as n equals 3. If we were to refer to the term before, we describe it as n minus 1, because n minus 1 would be the term before the one we're on. Now, what we're going to do with this is we're going to look at how it works with some physical examples. And I want to link it to some other areas of mathematics. Now, the first thing that you need to be aware of is that I could write these terms out in terms of these symbols. So the very first term would be a by itself. The second term would be a plus whatever the difference was between these terms, a plus d. Then after that we would have a plus 2d, and then we'd get some kind of term which generally speaks of what is going on for any particular term number we're on. So look, if this is the third term, there's a 2 in there. Now that was the second term, so this 2 appearing here I could represent as n minus 1, the third term, with a 2 there, n minus 1 would be equal to. So a plus n minus 1d should give us the value of any particular term in this sequence. Now there's a famous adage that Gauss came up with a way of adding together all of these terms, and he came up with it whilst he was a schoolboy. And his idea was this, that the sum of all of these terms was simply equal to a half n 2a plus n minus 1d. This was the term that he came up with of adding these terms together. And from this point of view, it looks like just a mathematical challenge to do so, but I'm going to point out in a minute about how we could actually use this in physics. A really important thing is that if this added together, say for example, these 3, and I wanted to know what this one was by itself, then I'd have to subtract from this total sum the sum of these 2, which would require us to refer to the term before the one we're on for all of our n terms. In fact, I could write it out like this: Sn minus Sn minus 1 is equal to a half n 2a plus n minus 1d minus the term, the sum before, of a half n minus 1 2a plus n minus 2d. And what you can see is that that is indeed equal to a plus n minus 1d. It tells us how big the individual term is that we're on at present. So how are we going to make this into something about physics? Well, what I want you to imagine is we're looking at velocity now, velocity and time. In the first interval of 1 second, and n equals 1 occurs there, we're at 2 meters per second, and then we go up to 4 meters per second at n equals 2, exactly the same as before, but I want you to imagine that this now represents an object's motion that has got non-constant velocity. It is accelerating at 2 meters per second squared. So what can we do? Well, what we're aware of is if this is a sequence of terms and they all represent the velocity, then this formula here, which is equal to the particular term we're on at the moment, of a plus n minus 1d. Let's just have a little look at that for a second. What do these represent within this context? Well, A would represent our initial quantity, our initial velocity. So in physics, we give that a different symbol. It's going to get complicated with the symbols because we're comparing two different systems of symbols here. But A, the initial velocity, would be given by the symbol u. And what we're going to add on to it is, well, n minus 1, what does that refer to? Well, that's actually a reference to which of these values within the sequence we're in. What you can see here is n minus 1 occurs, n equals 1 occurs after 1 second in. And so this actually represents our time. Each second increments n along by 1. And so this n minus 1 is actually a reference to the time that we're talking about. D represents the difference between each one of these, and that is equal to by how much the acceleration has increased. So how much the velocity has increased within that time interval, which is of course the acceleration. And so looking at that, u plus ta probably doesn't really mean very much to you. But if I recall that what this is telling me is the particular term in the series, and that term in the series is telling me the velocity of the object, then what I have is v is equal to u plus, switch those around, at. So the definition for acceleration can actually be found by understanding this term in the arithmetic series. Okay, so what can we then do next with it? Well, this is where it gets really interesting indeed. If we were to look at this and we were to consider this to carry on, then what we would know from calculus is that the area under this velocity time graph would give us the displacement. And that is actually due to many reasons, but the way I want to explain this to you is we have got non-constant velocity. And what I know is that my displacement is equal to velocity times time. But if your velocity is changing, then what you can do is you can take your average velocity over this time interval and times that by the time, and that would give you your displacement. So the average velocity times time. Your average velocity is just going to be the velocity you started with and the velocity you finished at divided by 2. So S is equal to u plus v over 2 times t. There is one of your Suvat relationships. Another one. But this is understood in terms of just deriving it straight from here. What does it mean in terms of arithmetic series? Well, let's have a little look. U, for example, is the first term of our arithmetic series, so we would call that A, and we're going to add it on to what we've decided V is in this notation. V is equal to A plus n minus 1d. We're going to divide it all by 2 and times it by the t term, which in this case is going to be n minus 1. But what we're going to do here is there is an issue that n equals 1 here, it's the first term, but it's not actually where time starts. We need time to start before that. So I'm going to use n here a little bit flexibly to refer to just my time scale. So I'm going to put an n just here, and you're going to see why in a minute to represent the time. So we have this formula here. We can now collect some terms, and so that's what we're going to do. We've got 2a now, so we're going to have s equals 2a plus n minus 1d, all multiplied by n and divided by 2. And what you can see that we have here is that this is equal to, when we put it in, it's equal to a half n 2a plus n minus 1d. And so by simple substitution into this, what we actually get is Gauss's formula for the sum of an arithmetic series. We get that again. And what it actually shows us is that the early pioneers like Galileo, whose equations these are, and people like Newton and Leibniz, who first introduced us to calculus, they could have also derived the terms and expressions for arithmetic series probably 100 years before Gauss actually discovered it by just exploring this avenue. But I want to do one last thing from this point here. If we take this, for example, and substitute some values back into it, S equals, so the 2's cancel there, so we have A by itself times by N, and we're going to add on, so here I'm going to exchange the N minus 1 to be N, so it represents our time starting at 0 rather than starting at 1. So we're going to have N, well it's going to be a half, and then N squared, and then D. Now you've never seen this before, or have you? Well, let's have a little look. S equals A was equal to the initial velocity u, N was equal to the time, plus a half, D was equal to the acceleration, and N was equal to time. There we have it. That is Galileo's expression for an accelerating object, finding the displacement of an accelerating object. Now, this is so trivial that it's almost totally overlooked. The idea that you can move between an arithmetic series and indeed the Suvat relationships means that these things are all connected. We could use arithmetic series to examine the motion of an accelerating object. And more widely, it also means that we can basically go through this translation where calculus could be described in terms of the formula for arithmetic series, and arithmetic series could be described in terms of the symbols and notation of calculus. This is the end.